All right, so sampling distributions of the sample mean. So big picture, what to keep in mind. A statistic is just any calculation we make from a sample. In this class, we're going to focus on two main statistics that come up often, right? So sample proportions, which we just kind of dealt with, and the other one is sample means, which we're going to talk about today. All right, so when we talk about populations, remember the notation for the mean is mu, and for the standard deviation is sigma. And then when we talk about samples, sample mean is x bar, sample standard deviation is going to be s. So how do the sampling distributions work for a mean and a standard deviation? Let me share that with you here in a little applet. So here's the idea. Say I have a population, and it doesn't even need to be normal, but this is what we call the parent population, right? This is if I'm omniscient and I know my population distribution, I'm going to change it so that it's not normal. Let's say the population is, and this could be any data that you want. Maybe this is people's height, okay? And so this is the population of, let's say, heights of every person in the world. If I were to go out and take a sample, let's say of size 5. Whoops, I just reset it. Let me change the parent population again. Okay. So I take a sample, a random sample from the population of size 5. You saw that drop down into my second graph here. This is my random sample. So these are 5 random people's heights. And then if I take their average, that's what's in blue right there. And so I could do another 5. 1, 2, 3, 4, 5. Boom. And that's their average there. And then I could continue doing so. And basically what I'm creating here is a sampling distribution of sample means on the bottom. Now the true population mean is up here. It's 17.11. Let's say I do this 10,000 times. Okay, so this is an approximate sampling distribution of sample means from this population. The true population mean is 17.11. The mean of my sampling distribution is 17.07. So notice, very close to the true population mean. Standard deviation is different than the population standard deviation. We'll talk about that. But one thing that's important to notice is that this sampling distribution of sample means is approximately normal, right? There's a normal curve. I fit over it. You can see that the sampling distribution of sample means very, very close to that. All right, so that gives us some intuition for this. Notice that it doesn't matter that my population is not normal in shape. This one is roughly, the sampling distribution is roughly normal in shape. All right, so let me give you some facts about sampling distributions of sample means. Let's do that here. All right, so it's also an unbiased estimator. So you're going to get that the mean of the sampling distribution of x bar is equal to the population mean in this case. So that just means if I take a bunch of samples and for each sample I calculate the sample mean, the distribution of sample means centers over the true population mean. which is mu in this case. And the standard deviation of x bar is given by this formula. So sigma x bar is the population standard deviation divided by the square root of your sample size. Once again, that's as long as the 10% condition is satisfied. So same 10% condition as we had to check for sample proportions, which is your sample size has to be less than 1/10 of the population size. And that's just so that we can consider the individuals in the sample to be independent of each other. All right, and these are formulas that are in your formula packet. So we know the center, we know the spread. So it's important to know this. As I just showed you in that applet, it does not matter if the population distribution is not normal. What will be true is that if your sample size is large enough, the shape of the sampling distribution will be normal, no matter what the shape of the population distribution is. And this comes from what we call the central limit theorem. And the central limit theorem just says when n is large, the sampling distribution of the sample mean, which is x bar, is approximately normal. So you do need to have that down because there will be some questions on the AP exam where they want you to cite the central limit theorem. And the questions will just be in the form, how do you know that the sampling distribution of x bar is normal? And the answer is the CLT, the central limit theorem. And that just says as long as your sample size is large enough, the sampling distribution will be approximately normal. So here's what I'm going to do. I'm going to change my sample size to be 2. I know they use capital N for sample size in this applet, which capital N usually means population size, but what they mean by these N's are sample size. So I'm going to change it to size 2. And so what I'm going to do is take this parent population, which is clearly right skewed. I'm going to take a sample of size 2. I'm going to average them. So I'm going to get a sample mean, and I'm going to drop that sample mean down into this third graph. So 1, 2, there's their average. 1, 2, there's their average. We're going to do that over and over again. Sample size 2 that's a really small sample size, right? So I want you to see the effect that has on the sampling distribution, which is going to be in blue on the third graph. So if I did this over and over again, I would get an approximate sampling distribution down here eventually. So I'm going to stop doing it animated. I'm going to just do 10,000. Boom. Okay. There's my approximate sampling distribution where I've taken 10,009 samples, basically. You can see the mean is still really close to the mean, the true mean. True mean being 8.08, sampling distribution mean being 8.13. But it's not very normal, right? Like you can see the normal curve here. It still kind of mimics the shape of the parent population. And that's because the sample size is so small. Let's do a different parent population. Let's do maybe like a bimodal one. Oh, shoot. All right, I'll make it bimodal. There we go. All right, so again, if I take a sample, 1, 2, 1, 2, take their average, 1, 2, take their average. Now I'm going to do that 10,000 times. Okay. So what you can see here, the sampling distribution is not normal, right? It's trying to be. It's like it's created this peak in the middle, right? But you can still see the other two peaks on the sides. As I increase the sample size, the sampling distribution will become more normal. That's what the central limit theorem says. So let's say I do samples of 5 instead of 2. So 1, 2, 3, 4, 5, take their average, and there's my sample mean. And I do that over and over again to create an approximate sampling distribution of sample means. Do it 10,000 times, boom. Now, more normal, right? Still not quite normal, but more normal than when my sample size was 2, right? You can still see a little bit of those modes on the side here. You can still see a little bit of those 2 peaks, but as I increase my sample size, my sampling distribution will get more and more normal. All right, so now let's change it to sample size 10. So now I'm taking a sample of 10, take their average. There it is. Do it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take their average. Let's do that 10,000 times. Okay, now we're pretty much normal, right? What about 25? Oh, this is going to take a long time. I shouldn't have animated this one. There we go. Do it 10,000 times. Okay, now it's really normal for the sampling distribution. So that's all the central limit theorem is saying. It's saying that as you increase the sample size, you can expect your sampling distribution to be more and more normal. All right, so what's the size where you can assume that normality in your sampling distribution? And the answer to that is 30, and that's just a rule of thumb. But this is the large counts condition for a sampling distribution of sample means. So remember, for sample proportions, it was that p times n has to be greater than or equal to 10, and then also 1 minus p times n has to be greater than or equal to 10. For a mean, it just is your sample size needs to be greater than or equal to 30. Then it's safe to assume the sampling distribution will be approximately normal. That's called the large counts condition. Now, one thing to note about this is you only need your sample size to be greater than or equal to 30 if the population is not normal. If it is normal, it doesn't matter what the sample size is. The sampling distribution will still be normal. So if I go back to this, all right, if I make my population distribution just normal, boom, there's my population. My sample size can be 2. So 1, 2 mean, 1, 2 mean. And when I create my sampling distribution, it will still be normal. So no matter what the sample size is, if the population is normal, the sampling distribution will be normal. But if the population is not normal, if it's skewed, or if it's some other shape, remember that if you have a sample of size 2, that's not big enough. Your sampling distribution is still going to be roughly skewed. But if your sample size is big, it will be roughly normal. And when I say big, I mean the sample size needs to be at least 30. So that's our large counts condition. All right. So now we've kind of summarized the sampling distribution of X bar. So if we take a bunch of samples of the same size, and for each sample we calculate the mean over and over again. So we have a bunch of sample means. Here's what we know about the sampling distribution. It will center over the true population mean, mu. The standard deviation of the sampling distribution will be the population standard deviation divided by the square root of your sample size, meaning it will get smaller with a larger sample size, which hopefully is intuitive, because if you take a larger sample, you're going to expect that the sample mean is going to give you better information about the population mean. So each sample mean would be closer to the population mean, which would cause your distribution to kind of contract around the population mean, right? It shrinks in as you increase the sample size. And then we also know that it should be approximately normal if, one, you know the population is normal, or two, if you don't know the population normal, if your sample size is greater than or equal to 30, it's safe to assume normality of your sampling distribution. I'm being meticulous about this because I want to make sure you understand that all that's under here is a bunch of sample means. Okay. Let's do an example. All right, at the Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. All right, without doing any calculations, explain which outcome is more likely. Randomly selecting a jar and finding that its contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average contents weigh less than 16 ounces. So do you think it's more likely that we select a single jar and find that its contents weigh less than 16 ounces, or 10 jars and find that the average weigh less than 16 ounces? So the answer there is going to be single. And the reasoning is we would expect more variability in weight out of a single jar than in the average of 10 jars. Right? So averaging 10 jars is going to be more likely to be closer to the true mean, which is 16.1 ounces. So there would probably be more variability if you just selected a single jar. All right, so find the probability of each event described above. All right, so here's what we're going to do. I'm going to say let x equal the weight of a randomly selected jar. All right, so then for the first event, the probability that a single jar is less than 16 ounces. Well, they tell us that the parent distribution, the distribution in the weight of jars, is approximately normal. So right away, we're allowed that the parent population is approximately normal, so we can make normal calculations with this. So if I know the parent population is approximately normal and it centers over 16.1, and I know that its standard deviation, it says, is approximately 0.15. And I'm looking for the probability that a randomly selected jar is less than 16 ounces. So I'm looking for that area. All right. So we're going to use normal CDF here, right? So normal CDF, we're going to give our lower bound at negative infinity. Our upper bound is 16. Our mean is 16.1, and our standard deviation is 0.15. Okay. Let's just pull up our calculator. We'll find normal CDF in the distribution menu, so that's second bars. There we go, normal CDF. Upper is 16, mean is 16.1, standard deviation is 0.15. All right, so about 25% probability. Great. So we found that the probability of randomly selecting a single jar and it weighing less than 16 ounces is about 25%. Now I want to find the probability of randomly selecting 10 jars and finding that their average weighs less than 16 ounces. So I conjectured in part A, I thought that that would be less likely to happen because if you get 10 jars, you have basically more information and your average, we would expect to be closer to the population mean, which is 16.1. So another way of saying that is I'd expect there to be more variability in a single jar than in the average of 10 jars. But let's see. So if we're looking at the average of 10 jars, the way I'm going to notate that, I'm looking for the probability that their average, the sample average, or X bar, is less than 16. All right, well, I know that this sampling distribution will also be normal. Because even though my sample size is less than 30, it's 10 in this case. Remember, since the population is normal, the sampling distribution will be normal no matter what the sample size. So what I want you to recognize is that we're theoretically thinking about if we took samples of size 10 over and over again and we computed their average each time. So take a sample of jars of size 10, compute the mean weight. Do that over and over again. The behavior of that sampling distribution would be this. It would still center over the true population mean, which is 16.1. The standard deviation, so sigma x bar, is going to be the population standard deviation, 0.15, divided by the square root of the sample size, so root 10 in this case. And then I'm looking for the probability, again, that I get a sample mean less than 16. So 16 is going to be over here somewhere. I'm looking for that area again. So we're going to do a similar calculation. We're still going to use normal CDF. My lower boundary is the same, negative infinity. My upper boundary is the same, positive 16. My mean is the same, still centered over 16.1, but my standard deviation has changed. Now it's 0.15 over root 10. All right, so let's see how that affects my probability. So the only thing that's changing is that this is becoming, instead of just 0.15, this is 0.15 divided by the square root of 10. There we go, and that goes down to about 0.018. So less than a 2% chance of selecting 10 jars and having them be less than, having their mean be less than 16 ounces.
But like is there like what's like a real life example of like why you would find like the mean of the sample of like the distribution? Yeah, like the super like in-depth one.
Okay. Yeah, we'll do a couple of
Okay.
examples of real life cases, but Riley, what? You can't imagine yourself being the manager at Peanutty Peanut Company and wanting to know what the mean weight of your jars of shelled dry roasted peanuts are? Yeah, we will do more in-depth real life examples, I promise. Here's not an important example. Well, I guess this would be important to cell phone companies, data distributors. So the number of texts sent during a typical day by a randomly selected high school student follows a right skewed distribution with a mean of 15 and a standard deviation of 35. So we're talking phone text. I remember in the last couple of years, I'm always like, that's a lot of text. And they're like, 15? I probably send 100 in a day. I was like, oh, I send like 3 to my wife, and that's it. Uh, Anyways, so let me sketch out the population here. So population is right skewed with a mean of 15. So the mean gets kind of pulled towards the skew. So let's say it's right about there. And then we also know that the population standard deviation in text is 35. Assuming students at your school are typical texters, how likely is it that a random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? All right. So if we talk about a sample of size 50, so n equals 50, if I were to sample 50 students over and over again and look at their average number of texts sent during the day, here's what I know. I know it should be approximately normal because even though the population distribution is skewed, this will be approximately normal by the central limit theorem since my sample size is greater than or equal to 30, right? So if I looked at the average number of texts sent by 50 students, here's what I know about that distribution. It should be approximately normal. It'll center over the true population mean. Sorry, I drew my x-axis so big that's bothering me. Which will be, what do they say, 15. And I know that the standard deviation can be found by doing population standard deviation, so 35 divided by the square root of my sample size, root 50. All right, so I can then make probability calculations based on that sampling distribution for the averages of 50 students. So this is an example I put in here because it'll come up in the AP exam pretty often where they don't ask us how likely is it that a random sample of 50 students will have an average of blank text in the last 24 hours. They say we'll have sent more than a total of 1,000 texts, but we can put this in the context of average. So if the 50 students send more than a total of 1,000 texts, how many do they send on average? Well, 1,000 texts per 50 students is an average of, what's 1,000 divided by 50? 20. That's 20 text per student, right? So there's my average. There's the X bar that I'm looking for. So 1,000 texts per 50 student is 20 texts per student on average. So really, to answer their question, I'm looking to answer this probability question. What's the probability of getting an X bar, in this case, that is greater than 20? So what's the probability that out of 50 students, there's more than an average of 20 texts per student? All right. And so since I've already stated that this is going to be a normal sampling distribution of sample means, we can set it up this way. So normal CDF, I'm looking for 20 is going to be somewhere over here to the right of 15, and I'm looking for that area. So my lower bound is 20. My upper bound is infinity. The mean of that sampling distribution will be the same as the mean of my population, so 15. And standard deviation is going to be 35 over root 50. Great. All right, so 20, infinity, but there's no infinity button on my calculator, so I'm just going to do a bunch of 9s. Mean is 15, and standard deviation is 35 over root 50. All right, so 0.156, so a little more than a 15% chance of that happening. Okay. So just like we did with proportions, sometimes we're going to be interested in comparing two distributions. And so in that case, we want to know about the sampling distribution of the difference in sample means. We did this with proportions as well. So choose a simple random sample. Oh, come on. Computer catch up here. There we go. Choose a simple random sample of size n1 from population 1 that has mean mu1 and standard deviation sigma 1, and then a simple random sample of size n2 from population 2 that has mean mu2 and standard deviation sigma 2. All right. If both population distributions are normal, the sampling distribution of x bar 1 minus x bar 2 will also be approximately normal. In other cases, so when their original populations are not normal, you can assume that the distribution of sample differences will be normal as long as both sample sizes are greater than 30. So you just need to check again that both large counts conditions are satisfied on both samples. The mean is intuitive. The mean of the sampling distribution will just be mu1 minus mu2. The sampling distribution, the standard deviation of that sampling distribution of difference in sample means is given by this formula, which again you will have in your formula packet, as long as both 10% conditions are satisfied, meaning both samples are not more than 10% of their respective populations. All right, I'll pause here so that I don't rush you. All right, let's see. So there's your visual when we're looking at the mean, or the sampling distribution of the difference in sample means. All right, so what does that actually look like? So here's our last example. The heights of young men follow a more normal distribution with a mean of 69.3 inches and a standard deviation of 2.8 inches. The heights of young women follow a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. So, suppose we select independent simple random samples of 16 young men and 9 young women and calculate the sample heights. So x bar m and x bar w. What is the shape of the sampling distribution x bar m minus x bar w and why? So it would be normal. And the reason is both populations are normal. So not because of the central limit theorem here, because we don't have large enough sample sizes. One's 16 and one's 9. But since we know that both individual populations are normal, it's safe to say that the sampling distribution of the difference in sample means will also be normal. Find the mean of the sampling distribution and show your work. So the mean of the sampling distribution of x bar m minus x bar w will equal just the difference in their population means, right? So it will equal the mean for men minus the mean for women, which is just, what, 69.3 minus 64.5, which is 4.8 inches. All right, find the standard deviation of the sampling distribution and show your work. All right, so sigma x bar m minus x bar w will equal, so just going back to our formulas. So it's just the square root of sigma squared 1 over n1 plus sigma squared 2 over n2. So for us, this is going to be root 2.8 squared over the sample size for men, which was 16, plus 2.5 squared over the sample size for women, which was 9. All right, I'm just going to pop that in the calculator. That comes out to about 1.09 inches. All right, and last thing I'll mention, okay, so what could I do with this? What possible reason would there be for this? But let's say I'm trying to compare men's heights to women's height, and I want to go, okay, well, what's the probability that the average man is taller than the average woman? So in a sample of these sizes, so what's the probability that I get an average male height larger than an average female height? I'm trying to answer that question. Well, I can answer that by subtracting the average female height to the other side, right? So that's the probability that x bar m minus x bar w is greater than 0. And I would be able to calculate that because I know that this difference in distribution should be approximately normal, and I know the mean and standard deviation. So I could just go, oh, okay, well, that's normal CDF, where the lower would be 0, the upper would be infinity. The mean is, what do we say, 4.8. The standard deviation is 1.09. And I can pop that in my calculator, and that should give me the probability that I get an average male height greater than an average female height. I would expect it to be relatively likely, since the male height is larger on average than the female height. What did we say the mean was? 4.8. Standard deviation about 1.0809. Yeah, so really close to 100% chance of your average male being taller than your average female, giving those statistics.